I'm beginning the recording right now. Are you ready for me to get started?
Let's go.
Okay, perfect. So welcome. A couple housekeeping and recording disclosure announcements. You've all been muted upon entry. Please remain on mute, and questions can be asked throughout the webcast via the chat feature. So be sure to utilize that. We'll be monitoring that throughout. The WebEx captions and highlight is enabled. You can use your WebEx assistant to turn them off on the bottom left of your screen. And we're recording today's webcast, and your participation is your consent. We will send a link with the deck and recording in the next few days. Okay. And then a couple safety announcements. Sorry about that. Okay. So our safety moment for today is appropriate for this time of year to prepare. Don't let the winter storm take you by surprise. Be sure to have your cell phone charger, first aid kit handy, jumper cables, waters and snacks, flashlight, basics on hand so that you're not caught off guard. And your emergency supply kit is in your car and ready to go. And this is because you never know when you will encounter winter weather or emergency exposure. Just great reminders there. And now I'm going to turn it over to Rob. Sorry about that.
Great, thanks, Amy. And being in California, I can attest that we're expected to have finally some significant rain this weekend. So good safety message, Amy. And thank you for all of our participants today. We know that December can be a very hectic and busy month. So appreciate your availability to join us in today's discussion, thinking about decarbonization pathways. I'm going to do a quick stage setting for you so you have an idea of what to expect today. And then Daniel and I will make some opening remarks before we jump into really the deeper conversation. And the deeper conversation gets into thinking about pathways to decarbonization, not only to the near term around 2030, but beyond that, thinking about the 2050 timeframe. And of course, some key themes that come out are around technology optionality and the importance that it plays in terms of being able to support resiliency, reliability, and affordability, as well as equity. And then, of course, the timing of the decarbonization objectives. Once again, it's economy-wide. It is not intended to be a power sector-only objective. It's the ultimate prize is decarbonization of the economy. So we will move from there with some general themes around decarbonization for 2030 and beyond. And then look at three different areas: the making of decarbonized supply, so the making of the power resources that will support decarbonization, the moving of that, the grid, the importance of reliability and resiliency in a decarbonized future, and then finally, ultimately from a utilities perspective, which is absolutely wonderful. What does all of this mean from a demand, load, and capacity perspective as our obligation to be the fuel provider of choice and many of the end-use applications increases over time, and the level of electrification of end-use increases? What's that impact on the utility? So great to have Seattle City Light join us to be able to talk about that perspective. Next slide, Amy. Just a few grounding remarks, and then I want to turn it over to Daniel Brooks to give some insight into what EPRI is doing in this particular area. But when we think about U.S. decarbonization goals, first of all, it's obviously a global decarbonization goal that we are focused on. And when you think about this, it is not just from the perspective of the power system, like I said, but the economy-wide objectives that we have. How do we achieve net zero economy-wide from a global perspective? And you can't talk about decarbonization if you're not also talking about reliability, resiliency, affordability, and ultimately equity also. Make sure no one is left behind in this transition. And as Arshad Mansour alluded to when he was presenting at COP26 in Glasgow just a month or so ago, the importance of innovation and global collaboration is going to be key for all of us if we're going to be successful in ultimately achieving not only cleaner electricity, but then the electrification and deployment of cleaner energy resources throughout our economy. So I do want to highlight that from a perspective that innovation, collaboration is critical to what we are trying to achieve today. But what helps us get going is some of what we see right now coming out in terms of the Infrastructure Investment Act that was recently passed by the U.S. Congress. We believe that there's significant dollars in here that can help jumpstart many of the areas that we are focused on that are going to be critical to overall economy-wide decarbonization. So we're excited to partner with many of our utilities, many of our government partners, many of our industry partners to make sure that we can maximize these investment dollars and help advance the decarbonization of the overall economy to meet objectives globally. So with that, Daniel, Amy, you want to advance us to the next slide? Let me turn it over to Daniel Brooks, our VP of EPRI's Integrated Grid and Energy Systems, to talk a little bit about what EPRI is doing in these areas. Daniel?
Yeah, thanks, Rob. Appreciate that. And Amy, you can go ahead and move to the next slide. I'm going to be fairly quick as well. The real rock stars here are the folks that are going to dig into the details in a minute on making, moving, and using. But I'll just start. Rob said, wanted to tell you a little bit about what EPRI is doing. And for those that may not know, and I think most of you on the call probably do, but EPRI, we're a not-for-profit, public good, science-based research institute that collaborates globally to provide solutions across the electricity sector, but increasingly across the energy sector as well. And really three areas that we do that. One's around technology. We have many research programs and efforts underway to develop new technology solutions across the entire electricity value chain, but also into the other energy sectors to be able to provide those solutions that are needed going forward. And we don't do that in a vacuum. We work very closely with many different external stakeholders, whether that be national labs, universities, other technical partners. We do that both internationally as well as domestically. And so that technology piece is a big part. The second thing is really around strategy, decision support. We have a pretty extensive subject matter expertise around modeling of the full energy system, the electricity sector in detail, the end-use portion of that. And we use that expertise and models and tools that we've developed to be able to support individual stakeholders for making decisions about how they actually optimize the investments that are going to be needed as they go forward to have an energy system that does provide for that sustainability, reliability, resiliency, and affordability that's going to be needed. And while as a not-for-profit entity, we don't do anything to advocate for policy, we are a trusted resource because of our independence, our subject matter expertise for not only industry, but also for policymakers and other stakeholders, regulators that are out there, financial community, to provide insights in terms of what the implications of various technology, policy, other factors may be as we go forward. And so, that's, as you move to the next slide, Amy, thinking about EPRI in those three areas, technology, strategy, as well as thought leadership, those are all at play in what our role is in the decarbonization of the full energy economy as we go forward. And what we sort of simplify it down to three things: making, moving, and using. Rob hit those already, and you're going to get a deep dive from the team coming up on those. But we have significant technology, planning, strategy, as well as demonstration, deployment, and thought leadership across all three of those areas of making, moving, and using. On the making side, we think primarily around the electricity sector, and certainly that's the case. We've got deep expertise and work going on to inform, what are the latest needs on the technology side from renewables, nuclear, developing, not only ensuring that we have sustained use of our existing nuclear that's critical as we go forward, but those advanced nuclear technologies, what's happening with carbon capture storage and what's needed to either retrofit or to build that new with natural gas as we go forward. And beyond just the electricity sector, the work that Jeffrey will talk about with our low carbon resources initiative, developing those technologies that are needed to help also to decarbonize other energy sectors as well. And then, once you have that source of energy from those technologies, being able to move that, again, primarily in the electricity sector with our transmission distribution infrastructure, all the modernization that's needed in terms of new sensors, new analytics, new situational awareness, visualization, automation, all of those capabilities that are needed to digitize as we go forward, and to have smart capabilities and to really reframe some of the aging equipment and the aging infrastructure that we have in a way that's going to allow us to not only be reliable and resilient, but to actually to accelerate the decarbonization that we have. Flexibility from distributed resources, from bulk storage, a lot that goes on there. And then even on the using side, we have significant research and expertise around transportation, buildings, industry, looking at the technologies, but also looking at how those are integrated and leveraged as we go forward. And so we have work that we're doing that we'll share more details about in the deeper dives that are coming up. And then there's that cross-cutting. Rob mentioned it several times, but reliability resiliency is the key. As we go forward, the electricity sector is foundational to decarbonizing the full energy economy. Our models show that, as much as 2 to 3 times of end-use energy for the electricity sector going forward as what it is today. And that just means much more of society is dependent on the reliability and the resiliency of the electricity sector. So that'll be key. But it's also affordability, it's equity, environmental justice, making sure that it's safe, sustainable, and obviously cyber is important as we become more digitized. Bottom line, there's a lot to be done. There's a lot of work that we're involved in, but collaboration and innovation is going to be a key, and look forward to hearing the discussion and questions that you all have from the deep dives that are coming up as we go forward. And so without further ado, I'll go ahead and hand off to, as Amy moves us to the next piece, Tom Wilson is going to jump in and talk to us a little bit about what some of our modeling shows that future looks like. So Tom, I'll hand to you.
Great, thank you, Daniel. So next slide, please, Amy. I'm going to basically, I've got about 10 minutes to touch on 4 different studies that we've done, 3 released in the last year and 1 forthcoming early in 2022. Many of the folks who actually led the technical work here are on the line. I'd like to acknowledge Jeff Blandford, John Beislein, David Young, and Needy Santon in particular, but many other folks I see on the line have actually contributed to this work either as technical contributors or advisors who helped comment on it and guide us in the right directions. I could usefully spend an hour on each one. We've actually spent multiple hours on each one with our advisors, but with 2 minutes each, I'll have to give you a quick introduction of what's in the reports and then maybe choose one highlight from each to really focus on. The first 3 reports on the left there look at decarbonization pathways, and I describe them as generally agnostic about policy. They assess what it would take, given efficient policy, to decarbonize. In the first one, to meet the U.S. 2030 goal of economy-wide 50% reduction from 2005 levels. The next one, looking at electric sector net zero, and the one coming out next year, looking at economy-wide net zero. The fourth report or area is really looking at policy implications, policy design, because having perfectly efficient policy is not the direction that most countries go in, and we know about the ongoing discussions there. So trying to understand the implications of the policy proposals that are on the table is the fourth area that I'd like to highlight. Next slide, please. So looking at the 50% reduction by 2030 target for the economy, this report really highlights the pace and scale of change that would be required. And one aspect of that is in this figure on the left, looking at capacity additions and capacity retirements that would have to take place to reach a goal of 50% reduction economy-wide. One thing you'll notice, the first column there is looking at additions and retirements over the last 10 years, 2010 to 2020. The right 3 look at a reference scenario which has current policies, and then the other 2 look at the 50% reduction policy. You immediately notice there's a lot of yellow and green there, and a lot of purple showing up. These capacity additions of solar, wind, and batteries. So the first highlight is that those would be quite large. If you wonder about the size of the current system, this shows how much we've added in the last 10 years. The size of the current system is around 1,150 gigawatts. So we're looking at about adding about half the system again in the next 10 years in these scenarios that achieve 50% reduction by 2030. One key assumption in this chart is that where it's economic, existing nuclear continues to operate. If you were to not have that nuclear operate, it would you'd need probably another 300 gigawatts of new capacity to replace it over the next 10 years. So quite aggressive. Not shown in this chart are the other bullet points on the right. Increased electrification. We're looking at scenarios that are basically adding about 20% to the current demand that we have today. So quite aggressive, mostly driven by light-duty transport and medium-duty transport demand for electricity. It would be much larger if it weren't for great efficiency gains that we anticipate and assume that will happen by 2030. So efficiency is really important in that also. With huge changes on the supply side, huge changes on the demand side, you obviously have a lot of T&D build out. Just connecting that 500, 600 gigawatts of new capacity requires a lot of transmission. Also, interregional transmission to try to take advantage of diversity of resources is really important. As we show and as most other scenarios show, we're looking at about a 20% build out of interregional transmission. And that raises the issue of institutional change. How do you do this? Traditionally, it takes about 7 to 10 years to build transmission at best. How do you get the processes to accelerate to allow this kind of build out? Understanding how markets work when you have a large percentage of your generation having zero or negative marginal cost. So understanding these things are really important, and it's institutional innovation as well as technical innovation that are needed to get us to 2030. The next slide, please. The next study looks at net zero for the electric sector, so just the electric sector, not looking economy-wide yet. And we had 3 basic scenarios that we highlighted here. One was a definition of net zero that included carbon capture and storage and the potential for carbon dioxide removal from the atmosphere. The second scenario had just nuclear and renewables, so carbon-free sources as a source of generation. And the third looked at renewables only. The key insight that I'd like to highlight here, again, it's a paper we spent hours talking about, is the technology innovation needed to support clean, firm generation over time. In the 100% renewable case, that is provided by hydrogen primarily in this particular scenario. It looks like a small little part of that upper right bar is hydrogen. That's the energy from hydrogen. The capacity for hydrogen turbines in this scenario is about 300 gigawatts of capacity. So it provides capacity when wind's not blowing, sun's not shining, but also provides very low energy overall, and as you can see from this chart. We also have a lot of batteries. The batteries are providing a lot of energy on a daily basis. The diurnal cycle of solar and diurnal cycles from wind being balanced by those batteries on a daily basis. So a lot of change there. As you look to the right, that scenario tends to be the most expensive. It is limiting technologies that you're allowed to use, and so very expensive. If you can only use carbon-free technologies, we see new nuclear playing a key role and expanding broadly, as well as maintaining the existing nuclear, also combining that with batteries and a little bit of hydrogen to get the system to work. And finally, if you have CCS, it's sort of a game changer. CCS provides 2 different benefits. One is reducing emissions from plants that use fossil fuels. You can get down to perhaps 98% capture or more that would effectively render them carbon-free. And the other thing is helping you remove carbon from the atmosphere, which allows you to offset remaining emissions where it's hard to reduce them. And so this is looking at net zero for the electric sector. I'd highlight for this that the hydrogen numbers here are just for keeping the power flowing, keeping the lights on, and not for things like industry and other activities, because we're only looking at electric sector, which is the focus, next slide, please, of our study next year. This gives you an idea. I think the thing to highlight for the study coming out next year on net zero economy-wide is that the whole system is so interconnected. It's interconnected today, but it will have to be much more interconnected in the future to provide reliable, affordable, clean energy. The electric sector will play that continuing role in providing clean electricity, also providing electrification that we've highlighted before, but in addition, potentially providing clean fuels to other sectors. You also need advances and reductions in those other sectors as well. So that's coming out early next year. If folks have an interest, please reach out to us. And finally, I'd like to close by the next slide looking at the idea of policy. The first three studies really assume sort of a carbon price somehow implemented that would help reduce emissions in the electric sector and across the economy. The real approach and pathway we'll take depends on policy design, and the details matter. The study that I highlighted on the first slide was one that looks at different forms of clean energy standards. The details of exactly how you define a clean energy standard dramatically affect the cost of generation, the cost of the policy, what types of energy are allowed, build out of transmission and distribution, regional outcomes, and who pays at the end of the day for the policy. And so EPRI has been very busy this year in trying to understand and track the policies. The winds have shifted perhaps every day and sometimes every week over the last year as to where policy might be headed, trying to understand that policy and compare it to these basic needs that we have for decarbonization, things that have to happen is a key part of our work as well. So with that, I'm going to turn it to others for a more detailed look. The first speaker will be Jeffrey Priest, who's going to talk about decarbonizing supply of generation. Jeffrey?
Thank you, Tom. And we'll go to the next slide. There are four key aspects to defining our focus on the transformation of energy supply. And as you've seen from Tom and heard from Rob and Daniel, the complexity of all this are going quite large. Energy supply will be unique to regional needs and societal priorities, which makes the availability of multiple pathways, the topic of today's presentation, multiple pathways and options so critical to how we reach these goals in the future. We also have to understand how technologies integrate into the existing systems over time, and then how in the future new infrastructure might be needed, which would be a vital aspect to meeting these targets. The transformation, though, is not only on energy resources. And so we have to keep a focus on the benefits that can be realized within our communities and for the environment more broadly. And lastly, we recognize that every step taken to decarbonize the electric sector has an impact on the energy economy more broadly, and it's the same the other way around. So it's critical we understand how the energy system can meet various goals in parallel with multiple sector needs. Next slide. Our research is focused on creating resources to help decision makers be confident in developing future energy portfolios, and then adding value to society's efforts to reach decarbonization targets. For wind, as you saw on the previous slide that Tom shared, comparing multiple scenarios, we see 2 to 3 times the rate of deployment potential in 2030 compared to 2020. For solar, which is similar to wind, anticipating significantly more rapid build out of solar PV plants over the next decade. For both of these two energy supply resources, we're focused on the economics for long-term operation, how we can improve life cycle, production, and sustainability, how improving asset management can be done by developing and deploying advanced monitoring and diagnostic technologies, and also on resiliency, ensuring that the grid as the grid becomes more decarbonized, these technologies are able to withstand severe conditions and meet the energy demand at the time that they're needed. For hydro, we're looking at ways to increase plant output. Getting an additional 8 to 10% would add 12 gigawatts of generating capacity. And in the near term, that's a significant advancement in this decarbonization goal. This 8 to 10% could be accomplished by improving turbine efficiency, increasing plant discharge, adding additional units, empowering non-powered dams, canals, and conduits. The theme of today is around options. And so we understand the role and we're seeing how rapid deployment of renewables is going to be critical over the next 10 years. And thinking about within the next decade and beyond, the lower 3 areas become also more important, but also represent a number of other challenges. For long duration energy storage today, nearly all energy storage is provided by pumped hydro. We're seeing a steady increase in deployment of 1 to 6 hour grid scale batteries, but the future electricity grid could likely depend heavily on variable renewable energy resources, which may require a variety of energy storage approaches to address the gaps in duration and output, response time, all while balancing cost and reliability. It's not likely that any one technology will solve the energy storage challenge, so we're investigating nearly 100 different technologies of various long duration types, ranging from mechanical, thermal, electrochemical, thermochemical, chemical such as hydrogen, and the roles that they could play with broader deployment. Carbon capture technologies are proven on commercial scale in many industries, including power generation. And as Tom mentioned, CCS is poised to meet decarbonization only if the technologies are deployed within this decade. A single CCS application for power generation could likely take 7 to 10 years of effort to finalize engineering designs, obtain approvals, test and confirm geological storage capabilities, and commission new systems. But applying CCS is an economy-wide approach that should be viewed as a near-term opportunity for faster deployment. We are learning from other parts of the energy economy to enable decarbonization within the power sector through the roles of technologies like CCS. Another area that has an economy-wide approach, but is not likely to be a significant near-term opportunity more broadly, is the production and use of low-carbon fuels. Hydrogen, ammonia, synthetic fuels, biofuels, and other potential energy supply resources that we're investigating through the Low Carbon Resources Initiative. Our focus is not only within the power sector, but in the role these fuels and energy carriers could play in achieving net zero emissions across the entire energy economy. And while no one can really say what the future of these fuels will be, we anticipate that no individual sector of the energy economy making significant progress without others also supporting and implementing the adoption of low carbon fuels. The question really becomes, how can we enable multiple options at the same time while maintaining the reliability, the resiliency, and the equity that we desire and anticipate this future energy system having for everyone going forward. To talk about another example of energy supply, I'll turn it over to Craig Stover, who leads the Advanced Nuclear Technology Program. Craig.
Great, thanks, Jeffrey. If we can go back to the first slide, I'll start by talking about the value of the existing nuclear fleet for decarbonization. In 2020, here in the US, we produced almost 800 million megawatt hours of carbon-free power with nuclear. That represents the majority of the carbon-free power made in the United States in 2020. And if you look at the graph, you can see that since 1995, the nuclear fleet has provided a really significant amount of the CO2 emissions, or of avoiding CO2 emissions. But you also see that, over the last 10 to 15 years, we've started retiring some of the plants in the nuclear fleet, and that makes meeting some of our carbon goals tough. But things are changing with the arrival of advanced reactors. And if we can go to the next slide. So advanced reactors are here, and if you read the news every day, you'll see another exciting announcement about another utility picking an advanced reactor technology around the world. There are lots of new projects beginning what feels like every week. But advanced reactors are fundamentally different from the previous generation of plants. They come in a variety of different sizes, and they have a lot of different attributes, including increased flexibility, long operating lives. Many of these designs are very small. We have the ability to reach unique communities with these designs. If we go to the next slide, you'll see that traditional nuclear plants we're familiar with today are large light water reactors. These are the gigawatt scale plants that represent the majority of the nuclear fleet around the world. But there are so many new types of nuclear plants coming online today, are coming available today. We have sodium fast reactors, molten salt reactors, high temperature gas cooled reactors, and microreactors. And these come in all shapes and sizes. So you can have microreactors of a 1 megawatt scale all the way up to gigawatt scale plants. They have different output temperatures. So for example, if you are going to do high temperature electrolysis, there might be a high temperature reactor that would fit your needs. But this also allows us to serve a lot of non-electric missions. So many now are looking at using nuclear plants to provide carbon-free fuel to decarbonize shipping on air, land, and sea. We're also, have the ability to use microreactors to reach remote communities. We're looking at using some of these smaller reactors to provide process heat, to do things like provide district energy. And so, these new designs are much different than what we're used to in the past with gigawatt scale reactors, and really allows us to reach many unique industries with this carbon-free option for power. Next slide. So in terms of what we're doing at EPRI to support advanced reactors, when we think about deploying this future fleet of nuclear plants, we have to think that we're going to fundamentally change the way we deploy these plants. And most of the challenges associated with building nuclear plants really are on the construction side of the project. It's really not the nuclear part of the project that makes building a nuclear plant tough. It's really building the building. And so we have a lot of work underway developing innovative construction technologies to fundamentally reinvent the way we build these plants. We're also trying to reinvent the supply chain. We have many demonstration projects underway right now demonstrating how we manufacture major nuclear components that can potentially reduce the fabrication time of those components by up to 80%. We're also qualifying unique fabrication methods such as additive manufacturing for nuclear applications. And we actually submitted last year the first ever code case to ASME for pressure retaining components made with additive for nuclear. We're also thinking about how we operate these plants. And so right now we're working on a project. We're developing the technical basis for the autonomous advanced reactor. So how can we get to a point where if we want to use a microreactor in a remote community, that you can have truly remote autonomous operations? We're working to develop the technical basis for that. And we're also working to develop the technical basis for a substantially reduced operating staff for these new technologies. And we're also looking at other innovative ways to reduce the costs, such as decoupling the nuclear island and the turbine island in these new designs. With these new robust designs, there's no reason why you can't build the balance of plant part of your nuclear plant like a commercial facility and potentially significantly reduce the cost of construction in that way. So in summary, as we look at these new designs, there are a lot of opportunities, and there's also a nuclear plant for every mission, in development today. And with that, we can move on to the next section. I believe Aidan's our next speaker.
Yes, hi, Craig. Thanks, Craig. So, hi, everyone. I'm going to talk about the transmission and distribution implications of this when you do take the clean energy mix that others were talking about already, like Tom mentioned, and looking at how do we actually deliver that in a reliable and resilient way to the customers. So the next slide kind of lays this out, and we've looked at some of these future studies and understanding the decarbonization goals. We're trying to think through and categorize what are the types of issues we're going to have to make sure we assess, ensure the technology is there to allow us to maintain reliability, not just in that future state when we look out to 2035 or 2050, but hour by hour from now until then. We've seen earlier this year the potential consequences if you can't maintain that reliability and resilience, and not just in normal conditions, but in extreme conditions as well. And when we think about it, we think from the perspective of very short time scales. Can you maintain stability as large events happen on the system, both on a more localized level, but also system-wide? And then up to kind of longer time scales. So Jeffrey talked about shifting energy across with something like hydrogen or long duration storage to use that to shift energy from periods when, say, renewables are abundant to when they're less available. We categorize that in a few different ways. The resource adequacy one, the top one, I'll talk a bit in a minute about it in a little bit more detail, but really trying to understand across the extreme temperature scenarios, not just what we've seen historically, but also what we expect into the future. Can we maintain that reliability to the standard required, or even potentially increase reliability as we electrify other energy systems? We may need to actually improve the reliability of the electric system because people are relying on it more. And then we think about the balancing issues. We do see in any future scenario a lot more wind and solar that's going to require things like energy storage, but also demand-side technologies that can provide some of the balancing flexibility. And to enable that, then you need to have that grid modernization. You need to be able to communicate and control with some of the demand-side resources. So trying to understand what that flexibility need is, and then ensuring we can actually access it, whether that's from distributed resources or from those new flexible bulk system resources. Howard's going to talk a little bit more about some of the transmission planning challenges, but certainly, as Tom alluded to, there's significant increase in the amount of transmission we're going to need to see on the system to move those renewables around. Even in cases when you have high amounts of DER, you're still seeing a lot of value with increased transmission. And then on the distribution side, as we do put in more distributed resources and electrification of demand, we're going to start needing to understand the increased implications on distribution. And then finally, on the stability side, when we think about those large events, do we have the control systems in place, and that's going to need to be developed in time. We have protection systems in place to make sure that we do have that the system responds as we desire, and that we do have we minimize or even eliminate losses and loss load and other aspects like that. So we are going to have a system that's very different, and the next slide starts getting into some of the things that we need to start doing when we think about those differences. One of the things in the top left there, and I think Howard's going to touch on some of the protection aspects, but we are going to be operating a system at very high non-synchronous penetration of resources that aren't traditional spinning mass resources, but have different characteristics to the current resources that are on the system. So we need a way to operate in a more decentralized fashion, communicating with far more devices, but also using some of these new technologies to provide the capabilities that we're used to getting from those resources that may not be around anymore. Tom talked about the market aspects earlier on, but making sure that those resources, the capabilities that we actually need. So in the past, we've needed energy and capacity and some small amount of services. That relative mix might change. Energy is still going to be important, but it could be abundant during certain times, and we might be more concerned about having energy sufficiency and flexibility, adequacy, and other aspects like that. So designing the markets and ensuring that we have those types of resources, and that we can encourage the innovation in the resources. And then the grid, in terms of things like the supply chain, it does take quite a while to build out the transmission system, not just from purely the infrastructure build out, but also some of the regulatory aspects, and making sure we can coordinate and understand where we're going as a system, so we can make those planning decisions in a proactive way. And that does require that efficient regulation as well. So a lot of what we've been looking at in the kind of studies then is integrating various planning functions, whether it's the longer term adequacy type assessment down into the grid stability, trying to understand how those interact with each other, so that we have a system that actually works across every hour of every year as we transition the energy system. And one example of that is on the next slide, on the resource adequacy concept. So when we do see this electricity share of final energy increasing, our current standard of kind of 1 day in 10 years, we've already seen where that may break down when we think about things like the gas network issues that were in after the winter storms early in the year. But as we do push more of the energy system to electricity, we will see that we may need to even look at reliability criteria and reliability metrics again. So we've been doing a lot of work to understand the improvements and the changes that are needed in the processes and tools for resource adequacy assessment. And I'll hand it off to Howard then to talk about some of the NERC activities.
Thanks, Aidan. As you can see on this next slide, this is a graphic that shows the planning process, and you can see every part of the planning process will be touched by the concerns for decarbonization. So the first part of it, looking at models, your tool capabilities and the actual model of the generation. We're finding right now planners are having a concern about whether or not these inverter-based resources, the new generations coming online, whether or not we have adequate models that sufficiently model their reactions on the system. And then you move into modeling practices. We've had traditional contingency definitions of large units going out and what the impact is on the system. Now we're going to have to redefine that and look more at looking at multiple small units that might be going out due to common mode failures, and how you look at that reaction on the system. And then finally, the next side would be the studies. We've traditionally looked at, just on peak and making sure that you can survive on peak scenarios. But we're beginning to see more and more that with this transition to decarbonization, you need to look not just at on-peak, but shoulder peaks and off-peak situations to ensure that during ramping situations that you have adequate resources online to be able to take care of the ramp up and the ramp down. And then finally, your reliability decisions. As we know, it's very difficult to build transmission, and so you may see more of a reliance upon corrective action plans and operational procedures to be able to survive through some of the studies that you've had in the planning process. And then in the next slide, you'll see that there are other considerations that planners will need to take into account for the planning process. And that's the next slide, please. And so historically, when we've looked at planning the system, there was a linear flow. Generation was connected to the transmission, and then transmission transported that energy to the load. But now in this new model, we have generation connected to the distribution and to the transmission side, and flows going back and forth. And that model and studying those scenarios are providing new challenges and new concerns for planners. And then some of the other considerations out there is we're going to, swiftly be getting into situations where during high penetration times of these decarbonized assets, fault levels are going to look very similar to load levels. There will be very smaller amounts of zero sequence current or fault current that's available. There's also the concern about adequate reactive resources, whether they be on the transmission side or the distribution side, and how those would be deployed. Under frequency load shedding will be another concern that both planners and operators will be concerned about, because as we look at traditional under frequency load shedding and shedding specific feeders, you'll now be shedding load and generation if you're not careful, and so you have to be very, very careful about coordinating your under frequency load shedding settings. And then finally, if you look at places where we might be able to do mass production of decarbonized generation, those are probably going to be, most certainly will be remote from load centers. So they would be out in areas that are far away from the urban locations. And so how do you transport that energy? And there's going to be probably some sort of a consideration between whether that should be AC or DC when you're talking about transporting massive amounts of generation for thousands of miles. That kind of summarizes what we're talking about from the moving scenario. Now we'll go on to the using, and I'll turn it over to Jamie Dunkley.
Okay, hi everybody, thanks for having me. So I'm Jamie Dunkley, and I'll be talking about a specific example of some work that we're doing with Seattle City Light, and I'd like to thank my counterpart at Seattle City Light, Stephanie Johnson, for joining as well. So we'll talk about kind of the motivations why Seattle was interested in doing work like this, some of the technical work that we did with them, and then how Seattle is planning on using this study, as well as future plans that they have as well. Next slide. So at this point, I'll introduce Stephanie Johnson, if you want to talk about the aspects as to why you guys engaged in with EPRI and this study.
Great. You can hear me okay?
Yep.
Okay. So my name is Stephanie Johnson. I am a strategic advisor at City Light in our electrification and strategic technology group. And I'm happy to be here today to tell you a little bit about the great experience we've had with EPRI. So the motivation for this study really came from we're getting so many questions related to electrification, and as decarbonization policies are advancing, there's people come to City Light and particularly within the city itself, because we're a city department, they ask, does City Light have the capacity to continue to serve our customers under all these electrification? And it's a question that we needed to have answered. And so we kicked this study off with EPRI about a year ago. And I would say kind of the meat of the project is really looking at, in this transition, what energy would be needed for the electrification of buildings, transportation, and then commercial and industrial applications within our service territory. And then kind of on the flip side, the question is, what's the capacity of City Light's distribution grid? And so I will say it's a pretty all-encompassing study, but we didn't take into account kind of transmission to get to City Light service territory. We also didn't make any assumptions regarding improvements in conservation or energy efficiency or kind of like smart things, because I think we wanted to understand really like what would the full impact be, because then as we start to consider additional programs, we can understand the benefits that they bring by offsetting some of those projects. We also don't look at cost. So this was kind of a heads up for what it is. But I think we got some great information, and Jamie's going to go through the details of the results, and then I will chat a little bit at the end to kind of tell you what we're doing with it. I'll give it back to Jamie.
Great, thanks, Stephanie. So next slide, please. So with this work, we're trying to target lots of different policies that are kind of floating around in the Seattle area, and so we focus on 3 different scenarios to look at. You know, the title of this slide is kind of 100%, or title of this section is 100% electrification. Can we do it? But we also looked at some other options. So here's just kind of a layout of what we're thinking about, and we have kind of moderate market advancement, so a little bit more aggressive than kind of business as usual. This rapid market advancement, and then full adoption of electric technologies. And that meant different things in the electric transportation section, as well as in the buildings and industry. But we chose these to line up with, and we worked closely with Seattle City Light to kind of figure out how to make these line up with their current objectives. So for example, the rapid market advancement lines up with the Climate Action Plan, Drive Clean Seattle, Seattle's Clean Transportation Electrification Blueprint. And then the kind of, for the third one, the full adoption, we were looking at lining up with the Green New Deal, which is also an objective of Seattle. So, and you can see in the chart on kind of the right, you know, this ranges from sort of 11% of passenger vehicles being electric to kind of down to the third scenario, all of the passenger vehicles, as well as medium and heavy duty vehicles being 100% electrified, with similar objectives in the buildings and industry section. So all of this to kind of get at Stephanie's first question, you know, if we're kind of abiding by all of these policies that are going kind of electric and decarbonized, can our grid handle it? Do we have the capacity to do it? So next slide, please. So this just shows I'll orient you here. So x-axis is 2020 to 2042. Y-axis is total terawatt hours. And these are the 3 different scenarios. So moderate, rapid, and full adoption. And you see the terawatt hours required each year to get to those goals. I have a note on the right here that the total system capacity is 23 terawatt hours. So on a very high level, when we look at the full system capacity, yes, we can electrify all of these things and we'll get there. But there's some subtleties with this, and I'll talk about that in a second. You know, there are time and place constraints associated with that kind of 23 terawatt hours. Next slide. And so this is an example of the full electrification scenarios. That's scenario 3, where everything's electrified, and broken down by the different sectors that we looked at. So kind of the take home here is you'll see in the orange and the blue that the buildings, industrial and residential, commercial, are kind of taking the lion's share of the total energy needed over time. However, the needs from transportation sector are not tiny. And what we see in Seattle is that kind of this almost 25% of total energy going to transportation is what we're seeing kind of nationwide as well, you know, in kind of future 100% electrification scenarios. Next slide. So what does this mean in terms of load shape? So many of you are familiar with a plot like this, but this is kind of a total load, so an 8760, looking at the load in 2030 for the full adoption scenario. So on the x-axis, we've got the full year, y-axis, megawatts. And what you'll note here, and kind of what we wanted to point out, is that you know, these peaks are much higher than what we saw in 2020. We have both the winter and the summer peak shown there. What I want to drive home here is that, and Stephanie alluded to this, you know, we'll be working more on kind of how to do this. But this doesn't include any smarts. So for example, from transportation, where I'm most familiar, you know, people plug in when they get home. And so this is kind of almost the worst case scenario where we're not trying to incentivize anyone to shift off peak or kind of manage charging in a certain way. So in this scenario where we've projected forward, yes, there's peak load growth quite a bit, but there are many opportunities here to reduce this in these scenarios as well. Next slide. Okay, so we looked at kind of what would be needed for the buildings and the transportation side of things. So what do we have? So we did a grid analysis as well to really answer the question, what capacity does the existing grid have for this additional electrified load? And I talked about kind of total terawatt hours where, yes, that's the answer is kind of yes on sort of a, without looking at the subtleties, but we wanted to look at space and time considerations as well. So we did a detailed system-wide load hosting capacity assessment that took the specific analysis down to the feeder and substation levels. Next slide. So kind of in a high-level viewpoint, looking at the total capacity of the grid, you see a year on the x-axis and available system capacity on the y-axis. We're in gigawatts. So the orange is the current load, and the blue is the available capacity for these electrified technologies. So there is a lot of space. However, you'll see in, in winter peak, for example, which Seattle's a winter peaking utility, there isn't, we're projecting 4.6 gigawatts needed, and we're kind of peaking at 2.6 as total their available capacity. So we drilled in a little bit more to understand kind of the time and the location constraints associated with this available capacity. So next slide. And there, we could talk for days about all of these, but the idea here is that we did detailed regional analysis of Seattle's grid to show these different constraints that I talked about. So quickly kind of going through these, what is the capacity, starting on the left, what is the capacity during the peak load? So if we took the whole year's worth of data at the certain feeders and found the peak load, what's available in that time for the additional electrified capacity? And so that's where you see a lot of red. So there is a lot of available capacity, but if you target that peak time, when would there be, or what kind of capacity is available there? It's significantly less than kind of other times. We looked at the capacity during min load hours. So you would imagine that if we chose a time throughout the whole year where we had minimum load already on that feeder, then yes, there's going to be a lot of available capacity. So this kind of just shows you the two extremes of minimum and then maximum capacity, depending on different time constraints. And then we also looked at energy. And so the idea here is that, is a certain technology constrained by the power that it needs, or can it be flexible so that it can draw power at different times to meet a certain energy constraint that might be existing? So here we just looked at the energy available across a whole year. And we also looked at the energy available on the lowest day. Again, kind of looking at those extremes where we might see regional differences and where there might be constraints on the grid. So this report is 250 pages. It has a lot of details there, but to show you that we did kind of detailed regional time and location specific analysis to kind of target where Seattle needs to be thinking about these electrified technologies. Next slide. Okay, so high level, big conclusions here. Building and grid, we already talked about it. They're kind of the majority, the lion's share of the load. There's lots of options for peak mitigation strategies, as I talked about, specifically looking at space heating, space cooling, and water heating. And there may be opportunities for kind of dual fuel options as we look about kind of reducing that peak. Next slide. And then for the grid, again, there's a lot of available capacity, but it depends on space and time. So understanding where loads will be coming in is really important. From the electric transportation perspective, passenger vehicles are going to be an early player, but transit buses will be coming online, and they're all going to be charging in probably one location or a couple locations. So keeping an eye there. To electrified transportation, lots of people like to go on long trips. So thinking about not only Seattle, but the areas around it to enable that long distance travel. And then thinking about how flexibility can be incorporated as well. So at this point, I'll hand it to Stephanie for some last comments on how they're planning on using this. Next slide.
So, if we're going back to kind of what the original question was, is does the grid have the capacity to handle this? I have had the pleasure of having the job of walking around and telling people, well, it depends. So, but I think that part of that that it depends answer is leading us to ask a lot more questions. And so, what else do we need to know as a part in order to understand that what's dependent there? And so, right now we're using kind of these initial results to inform our existing processes. So we've incorporated it into our load forecast for next year. We're talking about having a scenario with our IRP that uses the rapid market advancement scenario, and trying to figure out how we're going to incorporate it into our distribution planning processes as well. But we're also taking a deeper dive on some of the topics. And so we've just contracted with EPRI for a number of other kind of deeper dives on some of the modeling information. We're also doing a EV fleet analysis to get a better understanding of the impacts of what fleets will look like. And the third one, is additional grid analysis. So looking at transmission and looking at our planning limits to see if, there's maybe new ways that we can use our existing system to really maximize our value for customers. And so the other thing we're doing right now is informing a lot of stakeholders. So Jamie and I have been on the roadshow, as we've been calling it. And one day my fiance was like, I heard you say the same thing 3 times today. And I was like, yes, I did. So, but we've been lots and lots of interest in Washington from legislators, from interest groups, from Puget Sound Energy, who's our neighboring utility and the natural gas service provider in our service territory. We're talking to kind of our internal advisory group, so our environmental advisory group, scheduled to talk to our IRP group as well. And I think just generally it's been a really useful exercise for us in that I think there's some really high level takeaways that we can take it's like clearly as we start making policy and program decisions now, we know that conservation and efficient, everything that can be as efficient and flexible as possible is going to benefit us on those days when, we're more than double what our current peak is. And then for kind of everything else, how do we start thinking about planning to live in a world where we can help manage and serve our customers in the ways that they need to be served? So I think that's kind of it. There's a lot more to come.
That's
I
great.
think people
Stephanie.
are super sick of me, but just the beginning. So.
Yep. Thank you so much, Stephanie. At that, I'll hand it back to the group. Thanks.
Great, Jamie and Stephanie. One of the questions that came up before I provide my closing remarks, I did want to emphasize this equitable transition, and it was a question that came up in the chat about what EPRI doing in this area. So I'm going to turn it to Morgan Scott very quickly to talk about a group that she's leading around equitable decarbonization. Morgan, let me turn it over to you. I know you have a meeting tomorrow on this. So, Morgan?
Yeah, that's perfect. Thanks so much, Rob. That's exactly right. So as we think about these different pathways to net zero, when we think about deep decarbonization, we also want to be concurrently thinking about how do we leverage this clean energy transition to advance a more equitable future for all. And that's really thinking about the distribution of not just the costs, but also the benefits that come with this transition in consideration of vulnerable and disadvantaged communities today, but also historically. And so at the Institute earlier this summer, we launched our Equitable Decarbonization Initiative. As a part of that, we have had a series of technical workshops, and we actually have the final of the 6 workshops tomorrow. So tomorrow's topic is going to focus in on metrics and tools, something that I imagine resonates with many of you. What are the metrics that can be used to understand and quantify the benefits and impacts of this clean energy transition when we think about it through the equity lens? And what are the tools that are available to us to better understand those communities in need and really focus programs and policy? So we really invite everyone to join us. They are open workshops. I'm going to drop and just dropped the registration link into the chat. If you're able to make it, it's tomorrow from 1 to 4 p.m. Eastern. We welcome you to jump into the conversation. A great panel of speakers, plenty of time in the breakout sessions to have a good conversation with our attendees. So if there are any questions, I'll be in the chat and can answer them there.
Great. Thanks, Morgan. And just to close, I'm going to spend one quick minute to close. I think it was great to have Stephanie and Jamie wrap this up at the end, because one of the biggest concerns I hear within our industry, the electricity sector, is utilities will talk about the opportunity we have to be the provider of choice with clean energy going forward, but also then the obligation and the challenge we have to make sure that we are prepared to manage the societal, increased societal requests of us. And Daniel mentioned this earlier, when you look at electricity becoming a much greater share of final energy in the not too distant future, we need to be prepared for that transition going forward. And to prepare us for that transition, we talked about the need for innovation, whether it be on the supply side, whether it be on the grid side, or whether it be on the end use technology side. Innovation and collaboration are going to be key. And in order to enable that, we need to be actively engaged in these discussions and these processes today, not waiting till the day that they are expected of us as a group going forward. And then finally, once again, just to highlight and close, decarbonization important, but you can't think about it without thinking about reliability, resiliency, what it means to affordability, and then as Morgan just closed with, what it means to equity going forward. So we appreciate all of our speakers today. No good deed goes unpunished, and we wanted to make sure that you had access to them. If you had follow-up questions, the slide summarizes their contact information for each of them so that you can reach out independent of today's WebEx and contact them. Once again, thank you to all of our participants. Happy holidays to everyone. And hopefully, if you have the opportunity, please join us tomorrow for the Equitable Decarbonization webcast. Thanks again, everyone. Bye-bye.